Hello, we are Team 3 in the UConn Material Science and Engineering Senior Design Program, looking into the preparation of 3D printed plastic components for waterborne environments. Our project is sponsored by the Naval Undersea Warfare Center Division Newport, which is interested in 3D printed parts for use on unmanned undersea vehicles. 3D printed components can be easily created and stored, with the potential of one day putting a 3D printer on a submarine could fully eliminate the need to carry specific spare parts. Common issues faced when using plastic parts for naval applications include polymer degradation on exposure to seawater, and toxic off-gassing of parts which can damage the highly controlled environment of the submarine. To combat these concerns, as well as to accommodate constraints on mechanical properties and material availability, two sets of materials and coatings were selected.
The first material selected is ASA, or acrylonitrile styrene acrylate, a thermoplastic polymer that originated as an alternative for applications that employ its more famous plastic cousin ABS. As such, it shares many of the properties that make ABS attractive, including its toughness and performance under impact, with a few added benefits including resistance to UV radiation.
The next material is thermoplastic polyurethane, or TPU-92A. The 92A in its name indicates that TPU is one of the hardest materials in its class that is still able to retain the benefits of being flexible. This allows it to absorb significant energy before fracture and lengthen to around 3.5 times its original size before breaking. TPU-92A does not degrade rapidly in seawater or produce toxic fumes in normal industrial usage.
Both the TPU-92A and ASA samples were coated in XTC3D and XTC3D with UVO in an attempt to increase the impact toughness and water resistance of each sample. XTC3D is a commercially available epoxy coating, which can be combined with UVO colorants to increase the UV resistance of a material.
The sample set was divided into three groups, one for each of the aforementioned coatings and one left uncoated. Submerged samples spent 0, 2, or 4 cycles in seawater, with each cycle consisting of 3 days in the water and 1 day out. Tensile and impact tests were then carried out to ascertain how physical properties changed post-immersion. Tensile tests involve subjecting samples to an extended pull to get information on tensile strength, and impact testing involves swinging a pendulum hammer into the sample to see the energy absorbed before fracture.
The results of the mass data collected shows an increase in almost all the samples tested. This is thought to be due to a buildup of salt on the surface or a swelling of the polymers. Further testing is recommended to determine what caused this increase in mass. The samples showed almost no significant visual difference except for a buildup of a white residue on the surface, which is believed to be some of the leftover salt. Another interesting observation was the presence of biofouling on a small portion of the samples. This did not have an observable impact on our data, but is recommended to be further investigated.
ASA tensile samples exhibited a greater maximum tensile strength over TPU-92A samples. Although both uncoated sample sets did not exceed a 10% decrease in strength over 4 cycles of immersion, it should be noted that TPU-92A experienced high strains relative to ASA counterparts. Tensile samples overall contradicted the group's hypothesis, which was that uncoated samples would consistently degrade in strength at some rate with respect to time, and the addition of coatings would mitigate this effect. Rather, coated samples tended to actually be weaker than uncoated samples at all stages of experimentation. Moreover, many sample groupings actually experienced an overall increase of strength over time, with a sharp increase from 0 to 2 cycles and then a slight drop off from 2 to 4 cycles. These unusual findings may be due to a number of factors, including a faulty batch of 3D printed samples, deleterious surface reactions between coating and sample, and poor fracture mechanics, especially in regards to the TPU-92A samples.
The impact tested ASA fractured consistently within each time point and saw impact resistance values near 220 joules per meter. Both uncoated and coated, it saw a less than 10% decrease in impact resistance over the exposure cycles. The coated material, however, saw an initial decrease in mechanical properties from the as-received material, as was seen in tensile testing. The TPU-92A did not fracture through impact testing. Only a small crack was initiated below the notch on each sample. The coatings on the TPU-92A did flake off during testing. Overall, the ASA quantifiably retained its properties within the 10% success criteria, as did the TPU-92A. The XTC3D and XTC3D plus UVO coatings seem to succeed in waterproofing samples, but ultimately are not recommended for further use due to their rigidity and suspected chemical interactions with the ASA. While the TPU-92A was difficult to gather quantified data for, we believe this material shows the most promise for use by the Navy due to its remarkable flexibility and visually demonstrated durability throughout the study. Further testing is suggested to be conducted on fabricated parts to provide more accurate data.